This is the homework help video for Physics Homework 3.2. In her physics lab, Nicole rolls out a 1.0 gram marble down a ramp and off the table with a horizontal velocity of 1.2 meters per second. The marble falls in a cup placed 0.51 meters from the table's edge. How high is the table? Noticed obviously that I highlighted some stuff there. Let's go ahead and write down what we know. And let me set my pen up so it writes correctly. We know that Vix equals 1.2 meters per second. That's the first thing that we highlighted there. And notice that I'm adding the x piece in there. Remember, that's pretty important since we're looking at two different dimensions now. We know that Vy is 0 meters per second because it falls off the table. If we set up our scenario here, and I'm going to do this pretty small, we've got our marble, and it's going to go on a path somewhat like that. There's the 0.51 meters, and we're looking for that distance, so delta dy. We know that delta dx, there we go, equals 0.51 meters. And we know that we're looking for delta dy. The other things that we know here, we know that the acceleration is 10 meters per second squared down. And that's really just about all that we know. We don't really know anything else as far as we don't know the time, and there's nothing else that we would need to know. Okay, to solve this, there's a couple pretty important pieces here. The first thing that we're going to have to do is to use this Vix and the dx. And remember that velocity or speed equals distance over time. That's going to be pretty useful for us because we have to find the time before we can find anything else in this problem. So let's go ahead and plug some stuff in here. We've got 1.2 meters per second equals 0.51 meters over delta t. To solve this, remember we're going to flip these two, or multiply by delta t and divide by 1.2, and we should get delta t then equals 0.425 seconds. So delta t right here is 0.425 seconds. Okay, now we can go ahead and use one of those equations from the last unit. And in this case, we're going to use the delta d equals Viy delta t, that equation, the first equation for most of you on your note card. So I'll go ahead and write that, and I'm going to change colors here just so we can keep our stuff straight. We've got delta d, and remember this is delta dy, equals Viy delta t plus 1/2 a delta t squared. Now, in this case, our Viy is 0, so that can go goodbye. And we've got delta dy, or the height of the table, equals 1/2 times 10 meters per second squared times 0.425 seconds squared. Now it really gets somewhat easy. All we have to do is multiply 1/2 times 10 times 0.425 squared. Remember to square that 0.425 before you do anything else. And we should get delta dy equals 0.91 meters. Okay, here we've got Desi, and she's standing on a ladder picking apples in her grandfather's orchard. As she pulls each apple off the tree, she tosses it into a basket that sits on the ground 3 meters below at a horizontal distance of 2 meters from Desi. So we've got 3 meters here and 2 meters there. Oh, that's a nice M. There we go. And it says, how fast must Desi throw the apples horizontally in order for them to land in the basket? So this one is going to be very similar to our last problem, except kind of opposite. The things that we know here, we know delta D in both the y and the x directions. Delta dy is 3 meters, and delta dx is 2 meters. Time, don't know. Initial velocity in the x direction, that's what we're looking for. That's how fast must she throw the apples horizontally. Initial velocity in the y direction, that one's 0, so that one's a little bit easier. And then we also know that her the acceleration of those apples is going to be 10 meters per second squared down. So there's what we know. Again, we're going to have to work this one almost exactly backwards of the last problem. In the last problem, we used that delta D equation. We have to find time here in order to find speed. We have to find this in order to get that. Fortunately here, we know delta dy, we know acceleration, and we know initial velocity, so we can find the time. So we're going to use delta dy equals VIY delta t plus 1/2 a delta t squared. When we get all that, let's plug some stuff in. We've got 3.0 meters equals, this can all go away because there is no initial velocity in the y direction, equals 1/2 times 10 meters per second squared, and then delta t squared. Now I'm going to go ahead and divide by 5 here, the 1/2 times 10. So we're going to divide by 5 meters per second squared, and that's going to give us, that is going to give us 0.6 seconds squared equals delta t squared. The last piece here is just to square root, and we should get delta t, and I'm going to erase this for us now, delta t equals 0.77 seconds. So now we know the time that it takes for the apple to fall, and we also know the horizontal distance it falls right there, and we know that velocity equals distance over time. So all we have to do is take that 2.0 meters divided by 0.77 seconds, and we should get there 2.6 meters per second. So her initial velocity in the x direction, maybe I should have circled this piece too, should be 2.6 meters per second. Okay, here we've got Jack, and it's Jack be nimble, Jack be quick, Jack jump over a candlestick, with a velocity of 5 meters per second at an angle of 30 degrees to the horizontal. And it's asking us, did Jack burn his feet on the 0.25 meter high candlestick? The big thing here is to remember that this 0.25 meters is not necessarily his height, but it's the minimum height that he needs to reach. So we're going to have an initial velocity in the x direction that we're going to have to find, and an initial velocity in the y direction. We don't know either one of those yet. Now we do know that he had this 5 meters per second at 30 degrees to the horizontal. So let's go ahead and make a triangle here, and I'm going to redraw this triangle just so it's a little bit easier for us to work with. And remember, this is a 30, 60, 90 triangle in this case. So we've got 5.0 meters per second here, which means that the short leg of our triangle is going to be 2.5 meters per second. That piece is fairly easy. We can do the trig. I'm not going to. I believe that you guys can do that on your own. We'll have 4.3 meters per second for that leg. You could do sine, cosine, or tangent there. It really doesn't matter. You could also do Pythag if you wanted to. So our initial velocity in the x direction and outwards is that 4.3 meters per second. Our initial velocity in the y direction is 2.5 meters per second. Our minimum distance in the y direction, actually, no, we'll leave it that way, should be 0.25 meters. And I'm just going to put minimum for him not to burn his feet. His acceleration the entire time he's in the air is going to be 10 meters per second squared. And then we also know, and this is important, at the top of his jump, at the peak of his arc, at this point right here, his VF, or his final velocity, because we're just going to look at half the jump, VF in the y direction equals 0 meters per second. That is pretty important because that tells us what equation we want to use. We need an equation that has final velocity, initial velocity, distance, and acceleration, because we know nothing about the time that he's in the air at this point. So we're going to use VF squared equals VI squared plus 2a delta d. VF is 0, so VF squared is also going to be 0, equals VIY squared, so 2.5 meters per second squared, plus 2 times 10 meters per second squared, times delta dy. And I've missed a fairly important piece here, and I don't know if you've found it yet. Because his initial velocity is up, his acceleration is down, so we need to have a negative there on the 10. So it needs to be negative 10 meters per second squared. I apologize if that messes you up. When we go through the calculation pieces of this here, we're going to get 6.25 meters squared per second squared. Meters squared per second squared. Minus here, 20 meters per second squared delta dy. I'm going to move this piece over to the left side of the equation by adding the whole thing. So we're going to get 20 meters per second squared delta dy equals 6.25 meters squared per second squared. And then the last step of this is going to be to divide by 20 to get delta dy by itself. And we should get here delta dy equals 0.313 meters. With sig figs, I apologize, that should be only 0.31 meters. So yes, he gets over the candlestick. He does not burn his feet because his distance up is 0.31 meters and he only needed to go that 0.25 meters. Okay, for the last problem here, we've got Superman, who can leap tall buildings in a single bound, and we're asked how high a building could Superman jump over if he were to leave the ground with a speed of 60 meters per second at an angle of 75 degrees to the horizontal. We've got the triangle drawn up here, and I'm going to add one more line to this to help us out there. Now we've got our right triangle. We're going to solve this in a very, very similar way as we did the last problem on the video. We need to find his initial velocity in the x and y directions in order to solve this problem. So we're looking here for VIX and VIY. To do this, we're going to have to use a little bit of trig. So I'm going to use, in this case, I'm going to use sine of 75 equals VIY over 60, our hypotenuse. To solve that, all we're going to have to do here is multiply by 60. And we should get for VIY 57.96 meters per second. The other one, you can use Pythag. You can also use cosine to find VIX, and it would be 15.5 meters per second. The other things that we know here, we know its acceleration is negative 10 meters per second squared because his acceleration is down, his velocity is up. We don't know his distance in the y direction. That's really what we're looking for. How high a building could he jump over? We don't know anything about time. We do know that his final velocity at the top of his jump, we're going to look at the first half of the jump here, his final velocity up there is going to be 0 meters per second. So that's a fairly important thing for us to know. Again, we've got VF, VI, A, and delta D that we're looking for. So we're going to use that same equation as we did last time. We're going to use VF squared equals VI squared plus 2A delta D. Again, VF is 0, and we've got 57.96 now for our VI. Sorry, that's supposed to say meters per second. Plus 2 times negative 10 times delta D. When we square this, we're going to get 3,359 meters squared per second squared minus 20 meters per second squared delta D. Again, I'm going to move this piece over to the left side of the equation by adding it to both sides. So we're going to get 20 meters per second squared delta D equals 3,359 meters squared per second squared. And then the last step here is simply to divide by 20, and we should get here delta dy equals 168 meters. So Superman could jump over a 168 meter tall building. That's your homework help video for homework 3.2. I hope it helped.